This is Gerald Clark with Seven Planet Broadcasting, and today I've got a very exciting guest from London, Roland Michel Tremblay. How did I do on that pronunciation? Okay. And I stumbled across Roland while I was preparing my third series in a gravity series program. And it turns out what we're going to talk about today goes way beyond just gravity, but it was the entree into this program. I had read a book several years ago called The Final Theory, and many of you have probably heard me discuss it. I didn't go into detail real heavy because I was talking about ancient astronaut theory, so I didn't really feel that was the place. But as an engineer, this is very much near and dear to my heart, is knowing the true physical laws of what surrounds us, what operates life. And Roland turns out to have read not only the same book, The Final Theory by Mark McCutcheon, but he also is writing his own book called New Age Physics. Is that correct? New Age Physics, is that the right title? Okay. And he's written many yeah, he's written many screenplays, books. He's got 6 or 7 books now published in French. And you're just a prolific writer. And I could tell by interacting with you that you got a really good handle on what's going on, probably as much so as anybody I've ever discussed this expansion theory with. So today, Roland and I are going to kind of go through some of the questions that I posed for him. And I did this intentionally. I didn't re-review the book when I posed the questions because they were the old questions I had when I read the book the first time. And Roland came back and just blasted me with so much information. I felt like I wanted to get his perspective directly. So Roland, say hey to everybody. And anything I left out, not introducing you, tell them what you're all about.
Yeah, so just to say that The Final Theory is the book by Mark McCutcheon, and it's about the atomic expansion theory, and my book is New Age Physics, a theory of everything, which builds upon it. So it encompasses more what you would say the New Age or spiritual people and aliens are talking about when it comes to different dimensions, which Mark doesn't touch. So Mark is pure physics and how he can explain everything through the expansion of the atoms. And me, I take that further.
Yeah, that's actually where I guess you and I ended up kind of in the same camp. Is when I got a degree in electrical engineering and studied all the standard physics stuff and had Newton and Einstein stuck in my head. By the time I got out of college, you get out of college unless you're working in that space, you don't get to play with those models much anymore, right? So so I had kind of tucked those away until I saw this book, and I was a big fan of Richard Feynman and Kip Thorne, and not so much Stephen Hawking, even though I thought he was interesting. But I followed The Future of Space-Time, their book that they wrote out of Caltech about what they were going to do to try to pin down what gravity is. So I've always been kind of a hobbyist in this, but I don't think I've been as interested in it or spent as much time on it as you have. So I formulated some questions for you, and first of all, before we go into that, do you want to talk about just real briefly where we leave off with Newton and Einstein and why we went off to talking about a final theory, why there was a need for a new discussion of a new theory? And you don't have to. Go ahead.
Clearly, Einstein thought there was something wrong with Newton if he came up with his own general theory of relativity. And that now replaced Newton. But the problem with Einstein today is that to make his equations work and his theory works, we had to invent dark energy, dark matter, the Big Bang theory, from which it all came from, and gravitons or gravitational waves and all these things. And none of them are likely, and none of them, basically none of his equations or theories are actually matching with observations that we look at in the universe. So clearly there's something wrong with Einstein, and that is very clear. And with Newton, that we still use in our space programs today, if it was perfect, we wouldn't have to have countless cost calculations or corrections whenever we send something in space. So there is a problem there too. Also with Newton, there's a major problem, is that it defies the laws of conservation of energy. Where is this attracting force coming from? Does it emanate from matter? It's still unidentified, and none of it basically, Mark McCutcheon discusses all this in his book. He debunks the entire Newton's and the entire Einstein, and then he presents his theory. So at the end, they're all models of the universe that describe our physics, and they're all models that kind of work to a certain extent. And you can actually achieve these models just through observation and general data and statistics, and actually come up with equations in time that works. But at the end of the day, we don't perhaps have the real explanation that is required to explain everything. And when you consider expansion theory, from the fact that just the atom can be expanding all the time and the electrons as well, you can explain all of physics. Mark McCutcheon has rewritten the entire physics in his book, The Final Theory. And then at the end of the day, you look at these models and you see which one describes everything best, and then you realize that you decide which one is the right one. For example, with Mark McCutcheon, we can finally calculate for the first time through equations the gravitational force of the Newton, the big G, you know, universal things. This has never been done from calculations. It has always only been done from observation. Then, so from that point of view, you can see that there is a proof here. And there's so many proofs after proofs when you read the books that you can see, oh, that's why. Oh. And then suddenly all of these weird explanations from quantum mechanics goes. We don't have to explain the impossible, like quantum entanglement and things like that. So it all makes sense now.
You know, I was thinking about the sequence in which I asked you the questions. It now seems to make more sense to me to start by talking about what the four fundamental forces are for people, because most people don't know, and then starting from the inside at the atomic level from this expansion theory, and then working their way out. What do you think of that? So let me give my real quick understanding to people about what the four forces are, and then maybe you can launch into the atomic expansion theory, because we've mentioned it now, but people don't know what that is. Okay, you and I do, but they don't. Okay, so number one, when I was exposed to physics, I was taught there's four fundamental forces. There's the strong and weak nuclear force, electromagnetism, and gravity. And somehow the physicists had made these four distinct forces that somehow arose from the Big Bang theory, and that they were trying to unify and figure out how they all came from the same source, the grand unification theory, right? Well, with that said, we ended up with models that are still being taught in college that are 100 years old that truly do not fit, like Roland said, with what we actually see. They're just models of what the effect is, but they don't explain what it is, right? So why don't you talk about the expansion theory that you and I both got exposed to by Mark McCutcheon, and then let's start at the atomic level and do the strong, the weak, electricity and magnetism, and we'll end with gravity, because it's really the hardest one once you get into the orbits and the visualizations and the geometry to figure that out. Does that sound fair?
Yes, you know, there's one thing about these four fundamental forces of nature is that they were very arbitrarily designed in the beginning. You know, they were kind of four things that needed to be explained, but you know, the course for unifying these four forces into one thing, it seems like they are disparate things. They are disconnected, if you want. What is important is to explain what they are, you know, and then you can, through expansion theory, explain each of these things just by the fact that the atoms are expanding and the electrons as well. And so that's the unifying part of it, if you want, in expansion theory. So for gravity, for example, at the moment we've got this mostly Newton, where it's a force attracting at a distance. And then if you take Einstein, it's the whole universe is like a rubber sheet. And then, you know, if a big object is in the middle, then the smaller objects will actually kind of roll around like in a
I actually just did a simulation. I didn't give you the second one. A guy from a university had taken a big piece of lycra spandex and put it on a spherical hoop, put a weight in the middle, and was rolling balls of different sizes around on it, like the gravity well from Einstein as a visual aid. It was helpful, but it's just a visual aid, and it's not the truth. But keep going.
Well, they pretty much say this is the truth, because space-time and space-time mass energy is one concept in Einstein. They're all linked together, and this is where the time is relative. Now, none of this exists now in expansion theory. But there is another way to explain gravity. It is the fact that objects come closer together, and also objects fall onto the earth when you drop them. And this can be seen instead as a changing distance between two expanding objects. So the reason why objects attract each other is because the distance between them is reducing as they expand. And why an object is actually falling onto the Earth is because the Earth is expanding, like to catch up with the object. The object is actually free floating where you drop it. It's not falling to the Earth. The Earth comes up and catches up with it. This is the elevator effect of Einstein, which inspired expansion theory by Mark McCutcheon. So this is basically what gravity is. It's just the fact that everything is expanding. The atom, every atom is expanding at the same universal expansion rate. And so everything expands at the same time proportionally, so we don't see it. We cannot see this expansion, but it explains what we see if we imagine the concept behind it, that basically everything is expanding all the time, and the geometry of this expansion explains all the orbits and explains also gravity, the fact that objects will come closer together.
A couple of numbers came to my mind while you were talking about this. This is for our scientific listeners, I guess. That atomic expansion rate that turned out to be fixed exabay was something like 7.7 times 10 to the negative 7 meters per second square. Is that right? Or 10 to the 7 meters per second square?
I don't know the number exactly, but it sounds about right.
It was different than the 9.8 meters per second squared that Newton used, right? So it was very close to that, even though it was...
No, but that's the expansion rate of the atom.
Right.
You know, when you look at the Earth has got that many atoms in it, and then overall for the Earth, you know, it expands, you know, proportionally at 9.8 meters per second. This is still true because this is based on observation.
Right.
So this is an acceleration. So everything expands in an acceleration.
So you take the constant acceleration of expansion, x sub a, apply it to the geometry, and you end up with gravity, essentially is what you're saying. Or what the effect is that we feel of gravity is the expansion of anything coming close. So this is hard for people to wrap their head on. You want to do the beach ball expansion concept for people so they can get a visual of that, or do you want me to do it? The two beach balls on top of each other.
Cool, go ahead.
Okay. This one actually helped me a lot. For humans standing on the Earth, from expansion theory, if everything's expanding, this relative inability to see things expanding around you creeps you out, okay? It messes with your head. Let me put it on a gallery view here. So if you viewed the Earth as a beach ball that could be inflated, and you were a small beach ball standing on top of this, you know, and making contact without worrying about the closing distance thing. As the big beach ball was being inflated, the small beach ball is being inflated at the same rate, but because of force equals pressure times area, the force you're going to feel underneath you is the Earth pressing you up from that big beach ball. And that, to me, really helped me with the elevator experiment from Einstein, is to visualize this in terms of expansion, right? Yeah. That helped me. But then you took that little beach ball off some distance away where you started from geosynchronous orbit. If you just drop it, it was like, okay, why is it falling? And then this is where your Newton head gets stuck, right? But yes, we'll talk about all that. But
it's falling because the Earth is expanding towards it at a much higher rate than the ball itself is expanding.
Now, this part also got me really crazy, is when you actually calculate how fast I think it's like every 19 minutes, it doubles in size, something like that.
Everything doubles in size every 19 minutes.
That is a mind blower.
Although the expansion is an acceleration, at the end you still end up with the Earth getting bigger by 4.9 meters per second, and that's constant every second. You have to reestablish the geometry of expansion every moment by moment, every second, and then you look at the geometry then, and then you can see what's going to happen. That's why geosynchronous orbit, where you know the satellite doesn't appear to be moving, is that every moment you recalculate exactly where everything is, and it stays where it is. But that satellite is still going extremely fast. It's going fast enough to be on an orbit around the Earth, and it matches the rotation of the Earth. Exactly. But the idea that that's why it stays where it is. But in fact, you know, there's no difference between a geosynchronous orbit or any orbit. It's something that is moving away from us in a spiraling orbit. And then so when you can't see that the expansion, the space between the satellite and the Earth still remains the same, because the orbit behind the scenes, the gut viewpoint, is always enlarging, like a solar system.
And the satellite's expanding too. So it's just, or whatever, yeah.
Yes. So that explains why if an aircraft carrier is dropped from the sky and a small marble will arrive at the same time on the ground, because this is impossible in Newton.
Yeah,
so when
exactly.
the Earth is expanding towards it, of course, it will arrive at the same time. But even...
Oh, I'm sorry.
Yeah.
A good way to think about that is that aircraft carrier and that marble are floating in free space, just like the Earth. And
Yeah.
that the fact that they're expanding and they're the little beach ball, and the big beach ball is going to come up to meet them eventually. This is hard to grasp, but that's what's really, I believe, is the reason this is called the final theory.
Now, the problem with Newton is that you calculate the gravity based on the mass of the objects and from the center of these objects. In expansion theory, you calculate the gravity from surface to surface of the objects, and also the fact that the planet, if it was a styrofoam planet, would make no difference because the geometry of expansion will still be the same.
Mm-hmm.
So all our course corrections in space with Newton probably is that we don't know exactly the mass of any objects, and the gravity doesn't depend on the mass of the object. So that's kind of a proof that Newton was wrong. And we encounter similar problems with Einstein. So as you can see now, we have the chance to have real equations, the equations of Mark McCutcheon, that will precisely give us the perfect, we won't need any course corrections anymore. And we also know about the real gravity that we can expect wherever we go, because at the moment it's really hit and miss. When we went on the moon and we thought the gravity would be 1/4 of the Earth,
mm-hmm.
because the moon is 1/4 the size of the Earth, we got it completely wrong. It's a miracle that it actually landed, because it was not. It was 1/6 the gravity.
Yeah,
but what people don't realize is that on the other side of the moon, the gravity will also be different. It will be 5/6 of the gravity. You see? So I mean, no, it will be 3/4 of the gravity of the Earth.
Yeah, let me touch on this one. This one I must have missed during the first book. Is the difference in gravity as a function of the side which is expanding if it's being exposed to another body. So the opposite side of the moon is what Roland's saying will be expanding at a different rate because the near side is also being impinged upon. I don't explain the near side, why the gravity facing the sun is different. Is it because of the sun's expansion?
Because it's the Earth-Moon formation made the moon be more dense on our side than
mm-hmm.
it is on the other side.
Mm-hmm.
Or I think it's the opposite or whatever. But anyway, we go from the center of mass. And the center of mass is actually near us. So I guess, yeah. So near us, it's more dense and it's less dense on the other side.
Mm.
And since expansion goes from the center of mass, it starts at 1/4 perhaps of the moon up to the other side.
Right.
So, and then, although you could only calculate that when you are on the moon, and you cannot actually calculate that gravity from space because the moon still expands like a sphere in every direction.
Right.
You know, this density distribution and the center of mass makes it that it will be a different type of gravity on the other side. So I think I heard the Chinese are going to the other side of the moon soon.
I heard that too.
If you don't pay attention to this, they probably will crash. And then Americans will, I don't know, laugh about it. I don't know.
It'll be interesting to see what the dark side of the moon has to offer. Maybe they'll stay in low orbit first before they get too close and realize, hey, this is expanding different than we thought. So,
well, they've got to be careful because otherwise.
I know. I feel like we jumped past the 4 fundamental forces, went right to gravity, because that's the one that really gets us. Let's talk about the strong nuclear force from an expanding electron standpoint, and how changing charges could lead to what we call valence shells, and also it leads to chemical bonds that you pointed out very clearly. Do you want to talk about that real quick? So start with the strong and go to the weak.
The strong nuclear force is simply what is keeping the atoms from flying apart.
Exactly.
That's the big reason that they came up with some sort of strong nuclear force that, again, has no explanation, defies the laws of conservation of energy, and, you know, never really identified or anything.
Mm-hmm.
But if you look at the expansion of an atom, which is made of neutrons, protons, and the nucleus, and the orbiting electrons, in Mark McCutcheon, actually, the electrons are not orbiting; they are bouncing off the nucleus of the atom. So it's just that they are just expanding against each other, and as they expand from each other and they exchange electrons around them, or the electrons are bouncing, then there is no reason why it will actually fly apart. So we resolve that issue by the fact that they are all expanding against each other, they are pushing each other, and then the electrons are bouncing on top of that, and then the electrons would actually bounce from one atom to another, and then to another atom, and it will actually be bounded to form molecules. So that's basically how the strong nuclear force is explained in quantum in atomic expansion theory. So that's not a big mystery. Well, now we have identified what it is. There's no big force of nature there that is unknown, you know. So it's just that
this is one area where I think you're gonna discover things that may be different than somebody who only ascribes to the scientific principles. This is where I guess you reach the point where you keep asking why. Okay, if you ask yourself, why is an atom expanding? Why is this the case? What is the catalyst for that? We don't answer that with this theory, right? Because this is where it goes to something much bigger, some fundamental reason why matter would act this way. And in my opinion, that is encapsulated with what I would call the creator of all laws of matter in establishing the holographic universe, in essence. And that's a real scientific leap, which is not science, but
I will say that you're right when it comes to explain why the atoms are expanding or why the electrons are expanding. That can explain every phenomenon there are in physics. We have to go into philosophy or religion, you know, or spirituality. You know, they will actually, they are the fields of society that will explain why this, why that. You know.
Right.
But you know, it's very simple. If you get a computer and you do a virtual reality, you would have these objects on the screen. You will have, and they're all made of electrons. At the moment, it's all just electrons. But if you are programming the computer to actually form into protons and neutrons, because in expansion theory, everything is made of electrons. It's the only fundamental particle in nature. There may be neutrinos, but until it's really proven, you know, there are only electrons.
So you're not a fan of the particle zoo that's being developed over at CERN.
That people need to understand that all particles are just made of electrons. So you can smash them in any size you want and give them names that you want. But particles that exist only for a millisecond, is that a particle? You only want particles that can actually be stable in nature. Now, even the neutron is not that stable. It will decay, and you know, beta decay, which is, you know, the nuclear radiation thing. It would decay into a proton, a neutron, a neutrino, and actually and a proton.
Right.
So that's a neutron, you know, beta decay. So it's not very stable, and then it becomes more stable into a proton. But you can smash that proton and have two new particles there because they're all made of electrons.
Well, let's leave our atom smasher behind for a second. And now I think we kind of have a concept of small spherical protons, neutrons, electrons, and possibly neutrinos that are exchanging charge. Like you said, you got to have somebody that's taking care of the transfer of charge.
There is no charge. There are no more charges in atomic expansion theory. There's no positive or negative charge. Everything's explained just by the expansion and
I guess groupings of electrons, because they're always going to seek to dissipate their imbalance in polarity, if you will, from an ion back to a molecule, right? That's just what they do. So,
you know, that's actually one of the four fundamental force of nature. It's that electromagnetism, you know. And so that's very interesting because in atomic expansion theory, you know, electrons become clusters together. And then all clusters of electrons becomes light, radiant forms of energy, and then heat. And then if they actually are more distant, they're not in clusters, they are clouds. They are clouds of electrons. These are magnetic fields, and they are, magnetic fields are basically clouds of electrons. And then the movement of them from where there is a depletion of electrons and where there's a surplus of electrons, seeking balance, that creates all these movements. But even then, you know, Mark doesn't really talk about orbits of these particles like electrons, but I do, you know, in my book, because I think that that's a very interesting thing. It all obeys the same laws, whatever the scale. And, you know, we know that electrons are extremely small compared with atoms. So And, you know, atoms are concrete objects that we, you know, forms everything that exists around us. But electrons are much more, if you want, intangible. But I think they are more tangible than we think.
Can you relate the weak nuclear force to how chemical bonds take place? Because oftentimes you see in chemical equations, there's a balancing of various equations that essentially have ions joining to make molecules. So do you want to talk about that, or do you think that's clear enough relative to this theory?
Well, it's very simple. I mean, there are a certain number of electrons that will actually go around an atom. And then if another atom comes by with as one less electrons, then one electron will actually bounce between the nuclei of these two atoms.
Right.
And that's the chemical bond.
Right.
And so, and in certain conditions, then, you know, hydrogen will become something else, or, you know, another material will become something else. So it's very interesting. This is all very instant. That's very interesting. But so, you know, I have my theories that it's the same with electrons. I think that they probably are. They have a nucleus, and they have orbiting particles. For me, it orbits, it doesn't bounce. And I think that this is how they can actually join into clusters. This is how they can form a proton or a neutron. They also have particles exchanged between them that are called neutrinos, that actually can, because there's no charge, there's no positive or negative charges anymore. So it's got to all be the natural orbit effect of atomic expansion theory, and that explains all the atoms as well as the planets and stars and everything.
You know, this is probably not fair to you, but you're such a smart guy, I can ask you. In the concept of a electron versus a photon, how would you distinguish one, or how does one form together to create the other? In particular, electrons creating what we call a photon.
Well,
it's light.
Photons no longer exist in atomic expansion theory. Mm-hmm. A photon of light are just clusters of electrons. So little clusters together of electrons, and then they actually form, you know, these little particles. So that's why. So that's how I can explain it from the point of view of expansion theory, which is, you know.
Well,
it doesn't make much difference.
How would it emanate energy that we perceive as light?
Well, energy in atomic expansion theory is just the movement of electrons. It's just the expansion of electrons, mm-hmm. and the movement in either clouds or clusters. Right. And for Mark McCutcheon, there is no longer any kind of energy in the universe. It's matter.
Right.
All of it is matter.
Yeah, explain that a little bit, because this really caught me. It's like, wow, so light emanating from the sun, we call it all kind of things, a solar wind with all these ionized particles traveling. And all of a sudden, based on this expansion theory, what you just said is the entire universe is really an electric universe. And I've seen several authors essentially come to that conclusion. And in addition to that, because of that, if an electron is considered matter, then it's all matter. It's just in different forms. Am I right?
That's very interesting. Yes, it is true as well. And it doesn't make much difference whether, you know, you feel that energy is like photons and intangible, or if you think actually it's made of matter and electron clusters or electron clouds. It doesn't change anything. It's just a different way to see it or to explain it.
Do you have an explanation why there's a sinusoidal behavior of these clusters of electrons that are representing the electromagnetic spectrum in all its various forms? Why would it use this transmission medium? Is it because it's most efficient? I mean, what do you think?
Well, you know, if you actually light up a light bulb, then there's a reaction there. You actually free electrons from the atomic world, the subatomic world, and then they start expanding at an extremely high rate. And then they are pushing against each other, and then this is why light goes across the whole solar system and in its expansion. They're all electromagnetic spectrum. The only difference, first of all, you've got to understand that in atomic expansion theory, there are two different parts of the electromagnetic spectrum. They are totally different. The first part, you know, has got nothing to do with the second part.
Oh, really? Okay.
Yes. So one is actually more about electron clouds, and the other one is about electron clusters. So if we think about visible light, and I think before that is infrared, and then going higher into ultraviolet and all this until you reach the highest. The only difference is that there are more clusters passing by per second, the intensity, or they are larger clusters or smaller clusters. So that's the only difference to explain the different electromagnetic spectrums when it comes to the part where they are the clusters of electrons.
Mm.
And, I've got very interesting things about that in my book because
I'll bet you do. I'll bet you do.
that probably would be too complicated to get on here, but it's fascinating stuff. And this is the frequencies that people are talking about that comes from that, the different frequencies. And it's true, the frequencies, how many clusters of electrons there are, and how large they are. So that makes a difference.
I know where this is going, but I want to save that for a little while. So I'm going to do something that we can't probably visualize very well here, but I know there's 2 experiments and I read them, okay? But for people that want to know, okay, if all matter's expanding and I'm expanding, and the planet's expanding, and it's all doing it at the same rate, I can't detect it. How can I prove this to myself? And there's a couple of experiments that have been done involving a spring and a rubber band. Do you want to talk about those real quick? Just and give any insight to the merit of the pros and cons of this experiment, if you have them, because I think it's very, very profound.
I haven't read them again recently. I'm going to try to, from memory, to try to.
Okay, well, just do it.
I can probably still say a few things. Is that objects are free floating. So if you've got 2 balls with an elastic band, and then you drop them, the ball is there and the other ball is there, and you drop them. Well, logically, according to Newton, they should go poof, exactly the same. They should stay the same because they are attracted to the planet at the same time. But what happened is that the elastic band contracts because they are in free fall. They are free floating. They might as well be on a satellite, the International Space Station, because they actually contract as if there was no gravity at all, And then they get to the floor. Now, for the spring experiment, that's I can't remember exactly, but
it had to do with pulling the spring in such a way that one end ended up with the tines of the spring being farther apart than the other because of the same concept you're talking about. If gravity was actually pulling it down, it would stay distended, but no, it collapses back just like the elastic band. I think it's the same experiment.
Perhaps I will have to read it again. It's been a while.
Actually, yours, I think, is a bit better visual for me. I didn't realize there were 2 balls. I just had it in my mind that one ball was extended from an elastic band. You cut this, and then the band was short. But if gravity was pulling on them both the same, that wouldn't be the case. So
there is something as well that we didn't actually thought it was proof, but it's a little drop of water. When it drops from a branch, it immediately becomes a ball, but it could be explained by surface tension. But at the same time, it shows anyway that it's kind of in free fall. It becomes a little ball, like if it was on the International Space Station. And lots of water falling, usually can drop into as if they were free floating. So if you can check this, and it's very interesting that insects can walk on ceilings and on walls because the expansion of the walls and expansion of the ceiling downward is enough gravity for them to be able to stay there.
That's amazing, isn't it? Isn't that amazing?
This is just the beginning. There are so many things we can explain. And once this theory is recognized and lots of people are starting to work on it, there will be an industrial revolution. It could save the planet. So I think people should really pay attention, consider these new alternatives instead of, criticizing before they even read the book, as in the past, because there is a lot of potential here.
Well, I'm going to save 3 things for after our break. Faster than light communications, a space elevator, and the last one I'm going to make a surprise. Actually, no, I'll tell it now. You were leading up onto density changes in matter that lead to what we consider a dimension. And we're going to come back after the break and we'll talk a little bit about your concept of the density changes that lead to what we call dimensional realities, because I think this is an area where we both have a lot of interest. So you want to take a little nature break and catch up, and we'll come back and get back together and finish this up?
Yes, no problem.
Sound good. Okay, I'll put you on pause here and we'll come right back.